Hello guys, this is the second part of the grammars. Let's get started. In this section, we will go over the formal definition or let's say mathematical definition of grammars. Let's see what we got. A grammar can be defined by this quadruple. So let's go over each element one by one. So V is a non-empty finite set of the variables. Sigma is a non-empty and finite set of the symbols that we call them terminal alphabet. S is a special symbol that we call it starting variable or start variable. And P is a finite set of the production rules of the form this. So this form, yeah, we need to look into it a little bit with more detail. Look at the Z, and as you see here, Z belongs to this union of two sets, alphabet and the variables. And then we have a star here. So let's say, for example, we have alphabet as our famous alphabet A and B, and the V, which is the variables, it always has the S, and let's say it has A as well. All right, so what is the meaning of this? It will be the union of this guy, A and B, and S and A. And when we put a star here, it means that any combination of all of these elements. So for example, let's say AS, for example, or SAB, or SAA, and another B here. You see, any combination of the terminals and the variables. So this is the meaning of the Z. So on the right hand side, we can have any combination of the alphabet and the variables. How about on the left side? X and Y has the same thing. They belong to the same set. And we have one V1 here that is belongs to the variables. This means that on the left hand side, we need to have at least one variable because these X and Y can be even lambda or empty, right? But this V1 here that belongs to the variables guarantees that on the left side, we always have at least one variable, all right? Okay, so the note here is that in this course, on the left-hand side, we always have only one variable because when we put this combination on the left-hand side, it will be too complicated for this course. So that's beyond the scope of this course. One more time, on the left-hand side, always in this course, we will have one and only one variable. So one more time for just refreshing. So this is the set of the variables. This is the alphabet or terminals. This is the starting variable. And this is the set of production rules. Let me take an example here. We have this grammar here, and the question is, what are these elements? No problem. So the V is the S. Do we have any other variable here? No, just that S. Okay, so how about sigma? Sigma, the terminals are A or B. Yeah, just remember that this is, even though this is a terminal, but it's not an alphabet. That's our familiar empty string. How about a starting? Starting is that's just the S, this guy, and the only variable we have here. And how about the P? P is the set of production rules. How many production rule we have? It is S is defined as A, S, B, comma. What else? We have S is defined as lambda. This is the elements of this grammar. Now we are asking this question: what is the associated language to grammars? Yeah, based on our knowledge so far, you know that we can recursively produce some strings by the production rules. All right, as we said before and we learned so far, grammar can generate strings, and the set of all strings that a grammar can generate is called associated language to that grammar. And we denote that by L of G. Another question is when two grammars are equivalent. Again, based on our knowledge so far, I'm sure that you can guess what's the meaning of this and what's the definition of the equivalency of grammars. Two grammars are equivalent if both of them have the same associated language. L of G1 is equal to L of G2. If both of them has the same associated language, then we would say, hey, G1 and G2 are equivalent. Okay, let me take an example here. Are the following grammars G1 and G2 equivalent over this sigma? Let's understand what is the meaning of each one. Look at this one. It looks familiar to us. It is the B. We have both side of the A. And when we look at this guy, we know that this means any number of B's, right? So it means that on the left side of this A, we can have any number of B's, and on the right side, we can have any number of B's here. So what was the language that this grammar was constructed for? Yeah, it is all strings that has exactly one A. How about this one? This one looks like a little bit more interesting. So we have S is defined as BS and S defined as SB, and the third one is S is defined as A. So this is the actually terminator of this recursion. All right, so what does it mean here? It means that any number of B's, and then if we terminate this with A, it will be something like this, for example. All right, how about this one? This one is again any number of B's, but when we terminate that with the last S with A, we will have A here. And how about if we combine these two? Okay, let's combine one of them, A, B, S, right? And now, instead of this S, I will substitute this guy, which will be B, S, B. Fantastic. As you see, that we can have any number of B's on the left or right side. If we substitute this S with another BS, what would happen? It will be this, you see? So it means that on the left side, we can create any number of B's, and if we substitute the other one, this guy, then we will have any number of B's on the right side. And how can we terminate this recursion? With the last one, which is A. So do you agree that this grammar is the set of all strings that contains exactly one A? So if this is the case, you see that these two are equivalent because both of them are producing the same language. So theoretically, we can have infinite grammars for the same language. Now let's see what is the association between the grammars and languages. And you know that we are very interested in this relationship. We would like to know that how many formal languages will be covered by the grammars. So if we have the set of all grammars here, and we have the set of all formal languages here. Now the question is, what is the relationship between these two? definitely every grammar represents a language. Okay, so that language may be an empty language, but definitely every grammar represents a language. Is this the case that all of the languages will be covered by a grammar? Yeah, we still need more knowledge. Okay, so at least we can respond to one question here, that every grammar represents a language. In this section, we want to discover and define several types of the grammars. Let's see what we got here. So the first type is linear grammars. What's the definition of linear grammar? We learned that on the left side, we always have one and only one variable, right? But depends on what can we have on the right side, we can have different types of the grammars. For example, for linear grammars, we can have at most one variable on the right side. Look at this. V1 is defined as either a W, which is just a combination of the alphabet, or we can have W, V2, and U. So V2 is one variable. So when we say at most one variable, it means that either zero variable or one variable. Okay, so here is an example. Is the following grammar linear? Yeah, on the left side, definitely we always have one variable. On the right hand side here we have yes, yes, and yes, and yes. So the 0, 1, 1, and 1. So we would say yes, it is a linear grammar. What is right linear grammar? Right linear grammar is a linear grammar. So first condition is it should be a linear grammar, and second condition is the variable, if there exists, it should be on the right side of the terminals. Let me take an example. Look at this. First of all, is it a linear grammar? Yes, it is a linear grammar because on the right side we have at most one. And now, is this a right linear grammar? Yes, because the variable appears on the right side of the terminals. Similar to the right linear, we have left linear, right? And the variable should appear on the left side of the terminals. Is this a left linear grammar? Let's see. We have one variable here on the left side, and we have one variable here on the left side. I mean the combination of the terminals. And we have one here, yeah, and we don't have anything here. So all of those production rules that have a variable on the right-hand side, all of the variables appeared on the left part of the combination of the variable and terminals, right? So then we would say yes, it is a left linear grammar. Regular grammars. So a grammar is said to be regular if it is either right linear or left linear. Let me take an example. Is the following grammar regular? First of all, it should be linear. Yeah, it is linear, definitely. So we have only one variable here. And the second condition, it should be either right linear or left linear. Look at this one. Yeah, we don't have any terminal here, so we cannot decide it is left or right. How about this one? Yeah, the variable appears on the right side of the terminal. So this is the condition for the right linear. But when you look at this, it is the condition for the left linear. So this grammar is neither right linear nor left linear because all of the production rules should have the same characteristic, right? So this is not a regular grammar. We have this theorem that is saying that if we have a regular grammar, that regular grammar has a regular language as its associated language. So it means that regular grammar generates regular language. Fantastic. We have a new definition for the regular languages. It looks like that there is an association between regular languages and regular grammars. Let's see, we have another theorem. It is saying that if we have a regular language, then we can create a regular grammar for it. So it means that there is a tight association between the regular grammars and regular languages. So it means that we have now three different ways to represent regular languages: regular grammars, NFA, DFA, and regexes. All of them are creating regular languages. Okay, so now our knowledge is partially enough to represent this guy. Right now, we know that the regular grammars will produce regular languages. So far, we learned that if this is all of the formal languages, then the regular languages part will be covered by the regular grammars. Context-free grammar is another type of the grammars. Let's see what is its definition. A context-free grammar is defined by this format. Let's look at this format carefully. On the left-hand side, we always have one variable, and on the right-hand side, we have this V guy that belongs to this combination, and we already know what this combination is. It is any combination of the variables and the terminals. So recognizing the context-free grammars is so easy because on the left-hand side, we just need one variable. On the right hand side, we can have anything, right? Okay, so let me take an example. Is this a context free? Of course it is. Left hand side, we just have one variable, and the right side, we can have anything. Yes, it is. All right. Now let me ask a very interesting question here. Is a regular grammar a context free grammar? Yeah, you may pause the video and try to answer this question. What was regular grammar? We had this definition for the regular grammars. A grammar is regular if it is either right linear or left linear. And if you look at that definitions, then you would see that, yeah, on the left-hand side, they just have one variable. And on the right-hand side, we need to have a right linear or left linear. And it can be anything that we just said here, right? So, yes, a regular grammar is a context-free grammar. Now it's your turn to answer this question. Is a context-free grammar the regular grammar? Now let's take some examples, and during these examples, we try to sharpen our skills about the grammar as well. All right. Let's look at this. S is defined as ASA or BSB or lambda. Okay, so what is the request? Is G a context-free grammar? Yes, it is. Left-hand side, one variable. Right-hand side, anything. Yes, it is. And it is also asking what language it represents. All right. Okay, so for this purpose, we need to have L of G. Yeah, let's look at some of the strings and then try to find out or figure out what language it's representing. So S can derive lambda. So lambda is one string. How about this guy? If we have S derives A, S, A, and then we substitute this S with lambda, it will be AA. And how about this one? Yeah, with the same thing, we have BB. We still cannot figure out what language is this. We need more. So if we have this, and instead of this S with lambda, let's substitute it with the BSB and see what would happen. So A is here, and instead of this S, we would say BSB. And this lambda, what we get here, so it will be AB BA. Okay, so it means that the string of the left side and right side are reverse of each other. Yeah, if you try to produce or generate more strings, you will receive this language. L of G equal to W reverse such that W belongs to sigma star, and the sigma of course is here because we just have A and B, so it will be A and B. So this is the language that this is representing. So our answer is yes, it is context free, and the set builder of this language is like this. Another example, is this a context-free grammar? Yes, of course. Again, left-hand side, one variable, and the right side, we don't care. We can have anything, any combination of the variables and terminals. Yes, but it is still asking what language it represents. All right. So we need to have some strings here to be able to figure out what language it's representing. So definitely the lambda is one of them. And what else? We have SS here. Okay. Let's see. S derives SS, and then it derives. Okay, so if we substitute with one of these, what we get? We will get A, S, B, and let's substitute with another one, B, S, A. All right. So if we put lambda here, and we will get A, B, B, A. Is this the same WW reverse? Yeah, we need more investigation. How about S goes to SS and then A, S, B, and the same thing for the other S, A, S, B, and then lambda here, we will get AB, AB. Ah, no. So this is definitely is not WW reverse. All right. So it can be any combination of both of them. I mean WW or WW reverse. Is this the case? Yeah, we need more investigation. So S goes to SS, and then we can have ASB. Let's say ASB again. And now let's put this as an ASB again. It will be BB. So for this one, let's say it's BSA. All right. So it looks like that it is neither WW nor WW reverse, but for sure we know that when we add one A, we add a B as well. Okay, so all of these symmetric things is saying that when we add one A, we add one B, either left side or right side. So it means that we are getting this feeling that, hey, this is the language that number of A's and number of B's is always equal. Yeah, that's the case. If you're not convinced yet, then you can continue deriving some strings and then try to be convinced that, hey, this is the language. We would say it has some strings in such a way that number of A's of W is equal to number of B's of W. So this is the language, and we already responded that it is a context-free. All right, what is context-free language? Context-free language is a language produced by a context-free grammar. Yeah, so easy. So, and we call them CFL. All right. So a language L1 is said to be context-free if there exists a context-free grammar that produces it. So this means that in plain English that a context-free grammar produces a context-free language. Therefore, all of these examples that we have seen so far, A to the N, B to the N, WW reverse, and the one that we just learned, number of A's are equal to number of B's, all of them are context-free languages. Fantastic. Let's have a flashback here. Yeah, you remember when we were talking about PDAs, we said PDAs recognize the languages and their name is context free, right? And we were supposed to get back to this and explain that what's the meaning of the context free language. Now our knowledge is enough to understand that, hey, PDAs recognize context free languages, right? And we already knew that NFAs and DFAs recognize the regular languages. Okay, now I would like to mention the association between the machines, languages, and grammars. All right, DFAs and NFAs recognize regular languages, and we learn in grammars lecture that regular grammars generates regular languages. So this is the tight relationship between the machines, languages, and the grammars. We have another one for the PDAs. PDAs recognize context-free languages, and context-free grammars generate context-free languages. All right. So again, machine, language, and grammar. Now let's revisit the association between the grammars and the languages. If this is the set of all grammars, the set of all languages, so far we learned that regular grammars produce regular languages, and context-free grammars, which is a superset of the regular grammars, produce context-free languages. Before finishing this section, I would like to give you an idea that in some cases we can look at a language differently. What do I mean? For example, this language that we are so familiar since the beginning of the semester, A to the N, B to the N. Now I want to look at this language a little bit differently. How? So these A's and these B's should be always A's and B's? Of course not. If the alphabet looks like this, then the language looks like this. Lambda, A, B, A, B, B, and so forth, right? Now, if I change this alphabet to something else, let's see what would happen. So I would like to change this as left parenthesis and right parenthesis. So we can substitute any symbol here, right? Let's see, based on this alphabet, what this language look like. So lambda, yeah, left parenthesis, right parenthesis. Uh-huh. What else? Left, left, right, right. Uh-huh. Oh, very interesting. You see? And so forth, yeah? All right. What language is this? Very interesting. It looks like the nested parenthesis that it is being used in almost any programming language. All right. Okay. The next question is what string do not belong to this language? So it's easy, right? So for let's say L1 bar is something like this. For example, one left parenthesis. or one right parenthesis, or a parenthesis like this. You see, all of them are illegal in the programming languages. You see, this famous language that we have seen so far many, many times in this course, it has an application in programming languages. In this section, we want to talk about the hierarchy of the grammars. What does it mean? So far we learned that we have regular grammars, and a superset of these grammars is context-free grammars, right? We want to know that, do we have more? Okay, let's see. Let's start with this question. Can we create a context-free grammar for this language? A to the n, B to the n, C to the n. We just added C to the n. We already know that we can create a CFG for A to the n, B to the n, right? We just added one more. Yeah, you may pause the video and try to create a grammar for that. Okay, yeah, let's ask another question. WW. Can you create a CFG for that? I'm sure after some struggling, you couldn't. Why? Because the same reason that we couldn't create a PDA for these languages. And since there is an association between the machines and languages and grammars, this makes sense that we cannot create context-free grammars for these languages. Okay, let's look at the machines, languages, and grammars one more time. NFAs and DFAs recognize regular languages, and we just learned that we have regular grammars that represent regular languages. And also we learned that PDAs can recognize context-free languages, and we just learned that context-free grammars can produce them. Now, the question is, what kind of grammar will represent Turing recognizable languages? Very interesting, right? To answer this question, we would need to introduce two more types of the grammars. The first one is called context sensitive grammar. Okay, so let's focus on the production rule and look at this and just focus on this context sensitive. And we see on the left side, we have X and Y, and we have X and Y, the same X and Y, of course, on the right hand side as well. And what is the X and Y? X and Y is any combination of the variables and alphabets or terminals, right? So it means that we have a context, which is X and Y, on the left-hand side, and on the right-hand side, we need to have exactly the same context. So we have a context, and then we have a variable here that can be substituted to something else. All right. So that's why we call this grammar as context sensitive grammar. Can we take an example? Of course. So as you see here, A, B, and this S can goes to SS, B, C, right? And this one variable here can be substituted to AB. You see, all of the left side and right side should have exactly the same context. Here we don't have any context here. That's fine as well. Another grammar type is recursively enumerable grammar or unrestricted. All right. So let's look at its production rule format. We have X and Y here, and X and Y is saying that it can be any combination of the variables and alphabets or terminals. But on the right hand side, we can have anything. What does it mean that on the left hand side we said X and Y and the V1? So it wants to say that we can have anything. on the left-hand side because it's an unrestricted, right? This V1 is just guarantee that we need to have at least one variable on the left-hand side. And you know that if we don't have any variable, it does not make sense. If we have just terminals on the left-hand side, then we cannot substitute it with something. So definitely we need to have at least one variable on the left-hand side. All right, so this is really, really unrestricted, right? Because on the right side, we can have anything. On the left side, we can have anything. Just the only restriction is at least one variable. Okay, so and here is just an example. You see, here we have S, we have anything here, you see, on the left side, and the right side, there is absolutely no restriction. Okay, so this type of the grammar can produce Turing recognizable language. All right, based on this knowledge, let's look at one more time the machines, languages, and grammars. Now we know that we have here recursively enumerable grammars. Yeah, I think something is missing here. We introduced two new types of grammars. One of them was recursively enumerable, one of them was context sensitive. What happened to that? What kind of machine is associated with context sensitive grammars? Yeah, that's a good question. Yeah, we have one class of machines that is associated to this kind of grammar, but it is too complicated. And just remember that this grammar and this grammar is beyond the scope of this course, but I just mentioned that, and you need to know the names and the formats, but we don't have any further examples or further assignments for them. Okay, now we are ready to talk about the grammar's hierarchy that was introduced by Noam Chomsky. Let's see who is Noam Chomsky. This gentleman is an American linguist, philosopher, and historian. He's also famous for his political criticisms. He categorized formal grammars and introduced a hierarchy of grammars that is called after his name as Chomsky's hierarchy. And here is the four categories he introduced. He called the first one as type 0, that is recursively enumerable grammars or unrestricted. Type 1, context sensitive grammars. Type 2, context free grammars. And type 3 as regular grammars. As we mentioned before, these two are beyond the scope of this course, and we won't talk about that anymore, but we will focus on these two. I'm gonna stop here and see you guys in the next video.